So in this video, we're going to cover a head loss problem, including minor and major losses. Yeah, so let's do it. So in this problem, we're told we have this hydropower plant. We have water coming from this side of the dam, flowing down through our pipe, entering this turbine, and then out into just the other side of the dam. So basically, the turbine is taking this energy from the flow. We're producing energy with this setup. The turbine is outputting energy. So we're given some things about the problem. We're told some things, given some information. We're given H1 is 30 meters. H2 is 5 meters. What else are we given here? We're told we have steel pipe. Diameter is 4 meters. With roughness height here. Oh, sorry, so this is just D1. So just this first part of the pipe is 4 meters. And then we're told that this section of the pipe, so just this D1 portion, is 40 meters long. We have a contraction here with a 30-degree angle, and then our diameter here at D2 reduces to 1 meter. And then we're dealing with, it's 40 meters long, just like the other pipe. See what else. So the volume flow rate is equal to 6.28. So Q equals 6.28 meters cubed per second. And then we're given a turbine efficiency of 85%. And then just some other things. So epsilon 0.000 0.05 meters. And then we're also told density 1,000 kilograms per meter cubed. And then viscosity is 1.0 times 10 to the negative 3 kilograms over meters seconds. So the first thing that we're going to do here, the way I always start these problems, my first instinct is just to find my Reynolds number. So remember, a Reynolds number is defined as rho VD over mu. So if I plug in my knowns, I'm going to need to find velocity first, but I should be able to do that based on my volumetric flow rate. Note here as well that I'm going to have two different Reynolds numbers because I have two different diameters and two different velocities. So through this first section, we'll call this RE1. I'm going to use rho V1 D1 over mu. And then I'll also have a second Reynolds number, we'll call it RE2 equals rho V2 D2 over mu. So I need to find V1 and V2, and I should be able to do that using my volumetric flow rate. So if I remember, if I take a volumetric flow rate and divide it by an area, that gives me a velocity. So V1 is going to be equal to Q. I divide by pi over 4 D1 squared. V2, I'm going to do the same thing. Pi over 4 D2 squared. That gives me velocities for V1 and V2. I end up with 1/2 meter per second for V1 and 8 meters per second for V2. So I'll take these velocities and plug them in to find my Reynolds number. If I do that, I get Reynolds number, so RE1 is equal to, it's not quite 2 million, but it's, I mean, for practical purposes, we'll just say it's almost 2 million, approximately 2 million. And then our second Reynolds number, we have a Reynolds number almost 8 million. Sorry, let's fix that. This Reynolds number is almost 8 million. Both of these are greater than our critical value for laminar flow, which is about 2100, I believe, 2300. So we know we're dealing with turbulent flow in both of these cases. If I find my average roughnesses for this first section of the pipe and then the second section of the pipe, I can do that. I find epsilon over d1 and then epsilon over d2. If I work through that and solve that, I'm assuming that epsilon is this 0.00005 meters for both cases. So that gives me an average roughness here of 0.0000125 and then 0.0005. So I have the Reynolds numbers and I have the average roughnesses. What I can do, I hop over to my Moody chart. Right, you just have to pull up a Moody chart, and that's what you'll be given on the exam as well. So make sure you're comfortable reading a Moody chart. If I find, go to my Reynolds number, and then I find my curve corresponding to this average roughness and this average roughness, I get my friction factors. And these don't have to be super exact, just make sure you're in the ballpark. F1, I get 0.0108. F2, I get 0.0109. So I mean, you can see these are really close. But as long as you're in that ballpark, you should be good. So I found my friction factor for both pipes. What I'm going to do now is jump to my modified Bernoulli equation. So let's do that. I'll write the whole thing out here. Alpha 1. And I'm just writing out all these terms. Equals G, whoops, plus Z2, and then I'm going to include so my major loss, my minor losses, and then my turbine head as well. Yeah, so this is that modified Bernoulli's equation. So at this point, we'll make just a couple assumptions to simplify this Bernoulli's equation. If we assume station 1 is at this free surface here. Oh, whoops. Station 1 is this free surface here. What's going on there? Station 1 is this free surface here. Station 2 is this free surface here. Both of those should be just exposed to atmospheric pressure. So those are both 0. Or they're both the same, so they cancel. We're assuming that both of these bodies of water are reservoirs. And I mean, if we're dealing with a dam, that's a reasonable assumption. Meaning that V1 and V2 are both 0. And then we have, so the Z1 height here, H1, we have 30 meters. So this will become 30. Z2 becomes 5 meters. And then we just have to write out our expressions for our minor, major loss, and then our turbine head. So what we can do, we'll say 30, or I guess we'll say 25. Sorry, where'd my cursor go? 25 equals, so I'll write out just my term for major loss. And really, I'm going to have two separate major loss terms because I have two separate pipe sections of different diameters, right? We found two different friction factors for the two different sections of the pipe because they have different diameters. So what I'm really going to have, I'll have F1 L1 over D1, V1 squared over 2G, plus F2 L2 over D2, V2 squared over 2G. And then I have to include my minor losses. We'll work through those, and then my turbine head, which is what we're solving for. Sorry about that. I think my headset cut out again. But as I was saying, what we need to find now is an expression for our minor loss. This is going to be that expression for our major loss. We just got to figure out our minor losses now. So we can see here in this first section of the pipe, in terms of minor loss, we're going to have this here. We have this entrance, this sudden entrance. We have a contraction here. What else do we have? I think that might be it. Oh, and then this 45-degree bend. So remember, we have that expression for minor loss. What we do, we take the sum of the minor loss coefficients, and then we multiply that by v squared over 2g. And this gives us the total minor loss based on all of the different minor losses that take place. So if we expand it out for 1, what we would have, so we're going to have a coefficient for our entrance, and that says ENT, entrance, plus loss coefficient for that 45-degree bend, plus loss coefficient for that contraction. And then we'll multiply that by v1 squared over 2g. Let's see, so I'm going to move this, see if I can. Not easily. I'll do this one down here. So that's the expression for the minor loss in that first section of the pipe. Minor loss in the second section of the pipe, we're going to do the same deal. So in the second section of the pipe, I see I have a 45-degree bend, this long bend, the long radius 90-degree bend, and then I have this sudden expansion. So if I write that out, I'll have K45 plus K90 plus K exit times V2 squared over 2G. So these are my minor loss terms. What I would have to go do now is reference the textbook or at the internet somewhere. Or you'd be given these coefficients, I think. You would have to just check and see what the value of these coefficients are. I think they're all experimentally determined anyway, so you'd have to reference something to check them. And if we do that in this case, so this entrance coefficient ends up being right here. I'll just write it above 0.5. This 45-degree coefficient ends up being 0.4. And then this contraction coefficient ends up being 0.04. If I do the same thing for these coefficients, I have 45 again. It's going to be 0.4. This 90-degree long bend, I believe that coefficient should be about 0.6. And they might vary a little bit depending on where you look, but they should be around the same. And then the exit coefficient, we get 1. So we'd add up, 0.5 plus 0.4 plus 0.04, and then 0.4 plus 0.6 times or plus 1. Multiply it by v1 over 2g, v1 squared over 2g. We have v1, and then multiply it by v2 squared over 2g. We have v2. And if we add this hm1 and this hm2 together, that's going to give us the total sum of our minor losses. So we could take this, the sum of these, so hm1 plus hm2, and we're going to plug that in here, this hm. This is our minor loss expression. And again, the reason we have 2 of these, like 2 separate terms, is because our velocity changes. So we need to write out the minor head loss for each section of our pipe. If we had one long continuous pipe and no change in volume or velocity, we could have one long expression, but because we have a change in area, so a change in velocity, we have 2 separate terms that we'll add together. So if I plug these in for my minor loss, this plus this, all I'm left with is this turbine head term. I know V1, I know V2, I know L1, I know D1, D2, F1, and F2. We solved those at the very beginning. So if I plug everything in and solve for the turbine head, I'll do that down here. I should get a head value of about 17.03 meters. So this value, this is a head value, right? So what I really want, remember I'm trying to find my power output by my turbines. So the how much turbine or how much power my turbine is harvesting from this energy flow. So what I want to do is convert this value in head to a value in watts or kilowatts. And to do that, I can say that my power equals rho g q times head. So this is kind of the conversion factor, if you will, to get from head to power. So I know density, I know gravity, we know Q, that's that 6.28. So if I multiply this by 17.03, I get a power value of, what is that, like 1,048 kilowatts or so. But, so we're told that the turbine is only 85% efficient, meaning it's really only going to produce 85% of the theoretical energy that it would be producing. So what we would need to do to find the realistic power output, we're going to take this actual power and multiply it by our percent efficiency. So if I do that, my actual power ends up being closer to 891 kilowatts. So substantially less than my theoretical value. So that's how I would go through and solve a pipe flow problem with head loss. Remember, so with this problem, we had two different sections of pipe, and that's why we kind of had to break things up like we did. If you had just one long uniform section of pipe, you'd only have one Reynolds number, but we have a changing velocity, changing diameter, so our Reynolds numbers are going to change, and our friction factors are going to change. So that's why we had two terms for everything. So we had two major head loss terms, two minor head loss terms, which we just summed together. We found our turbine head, converted it to power, so we multiplied it by rho GQ, and then found our actual power, turbine power based on our turbine efficiency. So I think that's about it for this problem. If you have any questions, feel free to reach out before the midterm, and I'll do my best to get back to you by then. But other than that, I think that's it, so I'll talk to you guys later.